Okay, so today I'd like to welcome you back to Quantum Fluids in Isolation, and I'd like to welcome you to the talk by Dr. Christopher Hooley from University of St. Andrews. So Dr. Hooley got his Doctor of Philosophy from University of Oxford in 1999, and then from 1999 to 2000, he was a research fellow at Rutgers. From 2000 to 2005, he was a postdoc at the University of Birmingham in England. And from 2005 to 2013, he was a lecturer in the theoretical condensed matter physics at the University of St. Andrews. And then he was senior lecturer at the University of St. Andrews from 2009 to present. And also from 2009 to present, he was director of training in the Scottish Doctoral Training Centre for Condensed Matter Physics at St. Andrews, Edinburgh, and Heriot-Watt University in Scotland. So today he'll be talking about non-Fermi-liquids and applications of the functional renormalization group to non-Fermi-liquids. So please help me in welcoming, either by muting yourselves and clapping or by clapping virtually, Dr. Chris Hooley.
Excellent. So thank you very much, Joshua, and thank you for the invitation to talk here. Of course, it's 2 p.m. in Boston, but it's 7 p.m. in St. Andrews, so this is a nice evening seminar, although not quite post-dinner. The talk is about how to build a theory of non-Fermi liquids. This is a huge topic to which it's not going to be at all possible to do justice in the available time. I should also say at the beginning that the referencing on these slides is pretty basic and rather partial. Part of my reason for thinking I can get away with that is that most of what I'll be telling you about today has been published in these two papers that I cite here at the bottom of the screen. Therefore, if you want proper bibliographies, then please do go and look at those where we give much more detail as to where everything's coming from. Apologies in advance to anyone who is not cited where they should be on the slides, and I will try and remember it and at least mention relevant people. I should start with acknowledgements because there's never time to do them at any other point. So this work was carried out with two graduate students of mine, Sam Ridgway, who's pictured here on the left, and Matt Trott, who's pictured here on the right. This is my group photograph taken last year, believe it or not, at the height of summer, the famous Swilcan Bridge on the old course. And of course, we're grateful to the CMCDT and to UK Research and Innovation for funding to support this work. So here's the outline. I'll give a little bit of background about nearly ferromagnetic metals and the kind of experimental phenomena we're trying to describe. And then I'll start talking about how these things are often modeled. And that will lead us to section 3, which is actually quite a lengthy introduction that tries to cover some of the approaches that have been taken to describing non-Fermi liquids near ferromagnetic or nematic phases over the years. And that will serve as an introduction to our work, which is item 4, and essentially these 2 bullet points are the contents of the 2 papers that I mentioned in the title slide. The first thing I should say is that this is quite a technical talk. The reason it's quite technical is because I don't understand the physics well enough to give a simple toy model of how things work. Which is a shame, really. And you might say, well, if you don't understand the physics well enough to give a simple toy explanation of how things work, why don't you go away and work on it and then come back when you've got one of those toy explanations? But the fact is that actually it's been quite a long time since people started thinking about the non-Fermi liquid problem. And I think it's fair to say that we still don't really have those toy models, but we have to continue to talk about something. And so here is an attempt to express what we're trying to do, even though the work is not complete. And I certainly don't feel I have a good grasp on the basic physics. So to start with the background, here's the phase diagram of a particular material which has, or appears to have, a quantum phase transition to ferromagnetism. So this is uranium, cobalt, germanium. And you see in this phase diagram, there's a sort of ferromagnetically ordered metallic phase here, and as one increases the pressure, the ordering temperature drops and is heading towards 0 here, except it gets covered by this superconducting phase down here, which is actually quite common with these quantum critical points, you think that you're heading towards a zero temperature phase transition from an ordered state to a disordered state. Here we'll be interested in usually in a magnetically ordered metal or a pneumatically ordered metal versus a paramagnetic metal. But typically at low temperatures, and perhaps because of the enhanced fluctuations that happen in the vicinity of these quantum critical points, that tends to induce the formation of other subsidiary ordered phases, which actually end up masking the quantum critical point. And that may be completely universal as a statement, but even if it's not completely universal, it happens in a lot of materials. Here's alloy of nickel palladium, which also shows a transition from ferromagnet to paramagnet as a function of the nickel concentration. At very, very small nickel concentrations, does one lose the ferromagnetism? And so that's all reported on in this paper here. There's also uranium, rhodium, germanium. This illustrates another feature which comes up in at least some of these materials, which is that the transition to ferromagnetism, which was originally continuous, becomes discontinuous, i.e. first order at some point. And one can see that as a tricritical point, and then these wings of first order transitions branching off in the finite magnetic field plane and eventually leading to these quantum critical points out on the end of the wings here. So there's quite a lot of phenomenology going on in these ferromagnetic to paramagnetic metallic transitions. It's not completely clear how universal it all is, and this talk is not going to settle that question. I will be thinking principally about cases where the transition remains continuous, if not down to zero temperature, then at least down to the lowest temperature that we're interested in. And I'd be happy to discuss later if people want to talk about how often that is expected to happen. What do we see that makes us interested in these regions near the quantum critical points? Well, we see experimental observables that don't look like the standard theory of metals, which is Landau's theory of the Fermi-liquid. So for example, if we look at the electrical resistivity minus the zero temperature residual, here it is, for example, plotted against t to the 5/3, and the fit on that scale becomes almost linear here, which leads to an estimate of the exponent for the temperature dependence of the resistivity that is about 5/3, whereas at other dopings it's more like 2, and actually we start to get even stranger behavior further away. That's not just a set of signatures in transport properties. One also sees signatures in thermodynamic observables, like, for example, the specific heat capacity. So in a metal, regular Fermi-liquid metal, C over T would be constant as a function of temperature at low temperatures, whereas here we see that it's going up. This is a logarithmic scale, and so C over T is diverging like log of temperature, or such is the claim. So the question is, can we write theories that show, that predict this behavior, or more accurately, retrodict this behavior? And what's the essential physics of those theories? So let me start with, I think, some relatively uncontroversial bits, and then it will get more controversial as we go on. So what are we fundamentally starting with? We're starting with a bunch of electrons interacting with each other. So in the very simplest model, I could write that as a set of fermions with a regular free particle dispersion relation. Band theory is probably not crucially important to this stuff, so let me just write a free particle dispersion relation here. So this is just the kinetic energy term for these spinful fermions, and then I have a contact interaction, roughly, if we take screening into account, which is basically a density-density interaction between upspin fermions and downspin fermions. And we know from the Stoner mechanism that it's possible for that density-density interaction at sufficiently low densities or high interaction strengths to provoke a transition to ferromagnetism. Now, that's not the only way that ferromagnetism can happen in metals, but let's, for simplicity, stick with the case where that is the route that we take to ferromagnetism. And so we can Fourier transform this action, put everything into momentum and frequency space, and we can also do something which we very commonly do, which is to linearize this quadratic dispersion around the Fermi momentum. So if we're only looking at low energy excitations, if U is much smaller than the Fermi energy, then this is probably fine. And we expect that in a certain range of fillings, so for a certain range of Fermi momenta kf, this model will have a ferromagnetic metallic ground state, and in a certain other range it will have a paramagnetic metallic ground state. And so there should be a critical fermion density or a critical U equivalently, where there is a transition between the two. So this model at least has the two phases we're interested in, the ferromagnetic metal and the paramagnetic metal. And as written, it's a model of interacting fermions. But the problem with trying to treat this model is that the physics that we think is associated with the non-Fermi liquid is not very easy to see in this action. Right? The basic physical idea, if I flick back to one of our phase diagrams, is that as I get closer to the pressure where I get the quantum phase transition from the paramagnet to the ferromagnet, I start to get slow fluctuations of the magnetism in the material, which progressively slow down as I approach the ordering transition and then eventually freeze to make the ferromagnetic order. And the idea is basically that the physics of the non-Fermi liquid is the physics of those slow fluctuations interacting with the other low energy degrees of freedom in the problem, which are the conduction electrons that live on the Fermi surface. So our physical picture of this region has two types of excitation of the problem, basically. Fermionic excitations, which are the conduction electrons, and bosonic excitations, which are the collective magnetic fluctuations. And in this kind of action, we can't really see those two types of excitation. We just see a load of fermions, and any collective magnetic fluctuations will be complicated collective behaviors of those fermions. And so conventionally what people do is to say, well, we can always make a Hubbard-Stratonovich transformation to decouple this interaction term in terms of a field phi, and then we end up with a theory which looks like a sort of free term for the fermions, a free term for this bosonic field, which is representing the magnetic fluctuations, and then some Yukawa type interaction between the two. And that gets us to what we might call a fermion boson model, where we have an action for fermions, an action for bosons, which represent the slow magnetic fluctuations, and an interaction between the fermions and those boson modes. Notice that I've engaged in a bit of sleight of hand here, because when I first did the Hubbard-Stratonovich transformation, there was no kinetic term attached to these bosons. And so this boson term just has a constant in front of it. There's no omega, there's no Q or anything like that. But then in this action that I've written in the red box, suddenly there's a Q dependence to the inverse propagator of these bosons, and there's a mass for the bosons. And where did that come from? So it's not easy actually to fill in the steps between this line and this line. But the argument is that the low energy theory must look something like this, because the ferromagnetic ordering transition is then the condensation of these bosons, so that when this mass parameter R goes to 0, that's when the bosons condense and we go into the ferromagnetic metal. So I deliberately haven't put an arrow between this formula and this formula, because I don't exactly know how to do that arrow, but it's supposed to represent the early stages of renormalizing this theory here. And in that renormalization, the bosons will pick up some dynamics because they're scattering from the fermions, which already have some dynamics. And we know from the Stoner analysis that eventually the dynamics that the bosons pick up will cause them to condense, and that becomes the magnetically ordered phase. So all of our analysis in this talk is going to start from this kind of action in the red box, fermions with a dispersion relation linearized around the Fermi level, bosons with some inverse propagator, which looks basically like a Landau-Ginzburg expansion of the type that you would have at a magnetic transition in an insulator. And then crucially, this coupling between the magnetic fluctuations and the fermions. And the question is, what does that do? And the answer is that's actually quite complicated. So that's what the rest of the introduction is about. I should say, by the way, that I'm very happy to take questions at any time. So please don't feel if you want to ask a question that you have to wait to the end or wait for a pause. Just unmute and interrupt. I'm much happier discussing the audience's questions in a sense than presenting my own prejudices. Okay, so if we accept then that we've got to a model which describes the vicinity of the quantum critical point in terms of a set of fermions with a Fermi surface interacting with a set of bosonic fluctuations which are becoming massless as the critical point is approached, the question is, how do we actually describe the low energy behavior of a model like that? And the problem is basically we have too many soft fluctuations. We have gapless particle hole modes, right, which have to be gapless because the system is metallic, and we have gapless magnetic fluctuations, or at least magnetic fluctuations that are becoming gapless as we approach the critical point. So section 3 is an extended discussion, basically, of what one can do. I'm sure I've missed some things out here, so apologies to anyone in the audience whose favorite approach is not represented here, but here are a selection of possibilities. So I want to discuss 4 things that you could do with this model. The first of which is just, play dumb in some sense, forget about the physics you know, and just do regular Wilsonian renormalization group on this model, starting with no damping on the boson, which is the theory I wrote before. And I'll describe how you do that and say what some problems with it are. I'll mention Hertz-Millis theory, which has been very influential in this field. There one attempts to completely integrate out the conduction electrons and write a theory only in terms of the bosonic fluctuations and see what they do. So that gives a purely bosonic action with an overdamped boson. But there are some problems in renormalizing that theory, which I will refer to. Possibility C then, when one realizes that it's not so straightforward to renormalize a purely bosonic action, there's been a move in the past few years back towards actions that have the fermions and the bosons in together. And so I'll mention the possibility that you might try to do Hertz-Millis with the fermions put back in, so an overdamped boson plus some fermions with a Fermi surface. And then finally, I'll talk about sort of more diagrammatic approaches, which look at corrections to the fermionic self-energy when it scatters from this overdamped boson. My eventual conclusion of this introduction will be that it's at least not clear to me that any of these is yet working perfectly, which is the motivation for trying to do something based more on functional renormalization group, which I'll come on to in section 4. But let's first go through some of the things we could try. So the regular thing would be just to say, well, look, we've got an action here in the red box. Why don't we just renormalize it? We can put an upper cutoff on the momenta of the fermions, an upper cutoff on the momenta of the bosons, scale them all down and see what we get. And that's been done systematically in this paper by Liam Fitzpatrick and co-authors a few years ago. And the answer is you get a perfectly reasonable looking answer. You get a fixed point where the bosons are described by the Wilson-Fisher fixed point, the sort of regular fixed point for bosons below 4 dimensions. And you get a non-Fermi-liquid metal. So where the self-energy of the fermions does not go like omega squared, but goes, well, where the fermion decay rate does not go like energy squared, but has some other behavior. And this is done in an epsilon expansion, so expanding around 3 spatial dimensions, which is 4 space-time dimensions. And you find that the coupling between the fermions and the bosons is relevant, and so that carries you away from the weakly interacting theory, but it gets balanced by quantum corrections, and you end up at this fixed point. And the fermion self-energy here goes like omega to the 1 minus epsilon over 4. So if we go for 2 dimensions, so a sheet-like metal, then this would be 1 minus a quarter, so omega to the 3/4 self-energy. Okay, so that's one calculation you could do. Is it giving us the right answer? Almost certainly not, because in order to treat the model the way that they treat it, you have to ignore a piece of physics which doesn't turn up in the Wilsonian analysis of the model, which is Landau damping. So I'll say more about that on the next slide. Landau damping basically is this feature that if I have a magnetic fluctuation in a metal, then it can simply decay over time because it's made of mobile electrons which go sort of wandering off to the sides, and eventually any magnetic pattern that you imposed at time 0 gets damped away. So Fitzpatrick et al. Suppressed this by a large N extension of the model, but they can't suppress it exactly to 0. So what they're offering actually is a theory for a particular set of large N versions of the model I wrote earlier that doesn't go all the way down to t = 0 because it doesn't describe Landau damping. They also just suppress superconductivity by hand, which is why in their analysis you don't have to think about whether superconductivity really happens. Lots of the analyses I'll be showing here have found one way or another to avoid addressing the question of superconductivity, although obviously we know that that's likely to happen at low enough temperatures. So what's this Wilsonian RG missing? It's missing this feature, which I've drawn a cartoon of here, which is that if I impose a magnetic fluctuation of wave vector q on a metal, that means I put some excess upspin electrons in some places and some excess downspin electrons in other places, then over time, these electrons, of course, are going to move because this is a metal, and by the simple motion of the electrons, the magnetic fluctuation will be damped. And if I ask how quickly will it be damped, well, I can estimate that. The electrons are moving at the Fermi velocity. How far do they have to move before they damp out the fluctuation? Well, basically, the electrons from this maximum have to move into this minimum here. In other words, they have to move half a wavelength of the magnetic fluctuation itself. So the wavelength of that is 2 pi over mod q, so half a wavelength is pi over mod q. So the time it takes the magnetic fluctuation to decay is the distance they have to travel, pi over mod q, divided by the Fermi velocity, and therefore the decay rate looks like the Fermi velocity times mod q. Okay. So that's an important bit of physics that, you know, is right there in the perturbation theory, right? The moment you do second order perturbation theory in the coupling between the electrons and the magnetic fluctuations, you discover that the magnetic fluctuations can decay, and that's physical. They're decaying into particle hole modes of the metal. But this process does not come from an ultraviolet divergence somewhere in the Feynman diagrams. It comes rather from a sort of infrared resonance between two fermion lines in the diagrams. And so although it's an important physical process and it becomes dominant naively at sufficiently low energies, it's not the kind of process that regular renormalization schemes are designed to catch. And so the whole question becomes, how do you write a renormalization scheme that is appropriately sensitive to this damping physics, which has to set in at low energies, without just kind of writing in the answer that you want to get out? So the renormalization scheme should have the ability to show us Landau damping, but it shouldn't always show us Landau damping, because then in some sense we're just putting in the answer that we're expecting. Okay. So having realized that Landau damping is important, of course, one possibility is just to write it in by hand, and that's what Hertz did in 1976. So Hertz wrote a theory entirely in terms of the bosonic fluctuations, which we which he calls capital psi here. And you see this is the mass term which controls how far we are from the quantum critical point. This is the regular q squared momentum dependence. And now he's written in here the term that you get from second order perturbation theory. So if I start with the weakly coupled fermion boson model, and I do second order perturbation theory in the interaction between the fermions and the bosons, I get this dynamical term for the bosons, which at sufficiently low frequency always beats the omega squared that was here in the undamped theory. And so you see that's the issue. It's not that the prefactor of this term is divergent or anything like that. It's that however small the prefactor of this term is, at sufficiently low frequencies, it's going to dominate over an omega squared term because it has a lower power of frequency. And that strongly affects how you renormalize the theory, because if I had omega squared here in this frequency term, and I had q squared here, then to keep those terms competitive as I renormalize, I would have to scale the frequency like the momentum. That will give me a dynamical exponent of 1. Right? One says that the frequency scales like q to the z, where z is the dynamical exponent. So in this case, frequency would scale like q, and so z equals 1. Whereas in this theory, to keep the omega term competitive with the q squared term here, we have to scale omega like q to the power 3, right? Because we have to scale omega over q like q squared. And that gives us a dynamical exponent of 3, and that alters one's judgment as to which terms are relevant in the renormalization group and so on. So this is the sort of idea that Hertz put out in the 1970s, and Millis did some important follow-up work on that in the 1990s. And it's this theory that gives us a lot of the sort of standard predictions for the behavior of non-Fermi-liquid metals. So basically the statements about the resistivity exponents of t to the 3/2 near an antiferromagnetic quantum critical point, t to the 5/3 near a ferromagnetic quantum critical point, come from calculations that start from Hertz-Millis theory. But there are some assumptions embedded in here, and one of them is that when you think about the higher order interactions between the bosons, you don't have to worry really about complicated momentum dependence that they inherit from having integrated out the fermions. So Hertz points out in his paper that this is a conjecture which ought to be checked, and recently people have got further into checking it, and there are some issues, basically. So I refer here to Thier and Metzner, but there are other works on this, and those references will be following later. So briefly, to state the criticisms of the Hertz-Millis approach, it doesn't, obviously one criticism is it doesn't directly tell us anything about the behavior of the fermions in the non-Fermi-liquid because it's integrated them out. So if you want to know how, for example, electrical transport works, you have to find some way of pasting the fermions back into this purely bosonic theory. And there are some questions about how you do that. It's not actually self-consistent, right? It's used a Landau damping expression that comes from a Fermi-liquid form of the fermion propagators. But then if I recalculate the properties of the fermions, I find that they're not Fermi-liquid anymore because they're scattering off the magnetic fluctuations. Really, one ought to go around that loop until it converges, and that's not what's done here. Hertz-Millis theory is using just the perturbative form of the Landau damping term. And as I mentioned before, there are also problems with singularities in the interactions between the bosons, meaning that the power counting doesn't actually work out, which means that truncating the bosonic self-interaction at the 5⁴ term is on the face of it not okay. This may all be rescuable, but that's all I want to say about that approach for now. If you were worried about having left out the fermions, you could, of course, try to do the Hertz-Millis trick of putting in the Landau-damped propagator for the bosons, but keeping the fermions. So there's some work on this by Yamamoto and C and others. So this is to take an action which has the fermions and the boson and the Yukawa coupling between them, and ask, can we just do a Wilsonian RG on this problem? The answer is no, at least not naively, because the Yukawa coupling term doesn't preserve its form under the rescaling. And it's also pointed out that even if you could do this, the Landau damping term wouldn't renormalize. So yeah, so there are sort of issues about trying just to put the fermions back in and renormalize the theory in the normal way. It's not obviously renormalizable in the normal way. You can take patch approaches to this. I mentioned one paper here, but there are plenty of others. These patch theories have other undesirable features. In a sense, my view is they introduce a somewhat biased scaling based on one loop results. The fermion self-energy is the bosonic self-energy is calculated, put into the action, and then we look at the feedback on the fermions. It's not obvious that that's the right order of things. The patch approaches don't recover the Fermi-liquid, which one ought to get in some limits, and you can't get superconductivity in these approaches. The BCS coupling is always irrelevant. And that's an important point in a sense, because one of the whole questions about how to set such a theory as this up is, you know, I start off with a circular Fermi surface or a spherical Fermi surface if my system's three-dimensional, and the continuous nature of that Fermi surface is on the face of it important. Patch theories cut it up into pieces. Now, in antiferromagnetic models, that's often quite justifiable, because in antiferromagnetic models, there are particular bits of the Fermi surface that are strongly coupled to other bits at the ordering wave vector. But in ferromagnetic models, the ordering is uniform in space, which means its fluctuations are centered around Q equals 0, which means that all of the scattering is naively equally strong everywhere on the Fermi surface. And so these patch attempts are attempts to, you know, treat the entire Fermi surface, but continue to treat it as a set of discrete patches. And I would say this is where some of the difficulties come from, and why patch theories are problematic for Q equals 0 transitions in a way that they're not for example, transitions to antiferromagnetism. There's been an attempt also at a counter-term renormalization scheme. This is a very kind of high-energy approach to the problem, but I guess one should try everything. This was done by Taroba and Wang a few years ago. It's a very interesting analysis, but it has some strange features. There's a singular vertex correction, which comes from a sort of Ward identity about gauge invariance, even though this theory on the face of it doesn't contain gauge fields. They also make an ansatz of momentum-independent beta functions, which is, I mean, certainly not justified. So I'm not doing this calculation down, but I think it raises some questions that one still needs to try and deal with. And finally, I want to mention some calculations that have been done in more diagrammatic terms, which are in the spirit of, you know, let's take the Hertz-Millis bosonic behavior and try to see what it does back on the fermions and ask if we can reach something self-consistent. So if I make the simplest calculation, which is the self-energy of a fermion, so here this is a Fermi-liquid fermion, but this is a Landau damped magnetic fluctuation. So I'm asking what self-energy do the fermions pick up from scattering from a Landau damped magnetic fluctuation? And the answer is that it's an omega to the 2/3 self-energy. And then there's a question, well, okay, that's at the lowest order in perturbation theory, but does that omega to the 2/3 survive to all orders? And there's a literature on this as well. I'm pleased to see one of the authors I'm citing here in the audience. So there's a claim from Rekpepan and Chubukov in 2006 that the answer is yes, and Fermi surface curvature keeps the higher order diagrams small. But then Sung-Sik Lee points out in 2009 that actually the curvature cancels in a subset of diagrams, and so the counting is not so simple. And Metlitsky, sorry, Subir, I've misspelled your name here. Metlitsky and Sachdev in 2010 point out that there are some higher order diagrams which pick up logarithms in omega. And so there's a complicated story also that unrolls from this. Right. Let's take stock. That was a lengthy introduction, but it was quite deliberately lengthy because I wanted to make sure that I laid out before you some of the important threads in this story and explain why the story is complicated. So what I'm going to do now is to talk about the two pieces of work that we've done. And yeah, the 2015 PRL and the 2018 PRB Rapid. And I should say up front that this approach of functional renormalization group was very much inspired by the paper by Lee, Strack, and Sachdev in 2013, which was applying this kind of approach to an antiferromagnet. And so our thought was, can we get some interesting physics on the ferromagnet out from the same kind of technique? And so the distinction between the two bits of work I'll present is that the first piece of work, we were trying to write a renormalization scheme where we wouldn't have to write in Landau damping effectively by hand. In the first piece of work, we fail at that. So we do have to write in Landau damping effectively by hand, but we still find an interesting new fix point. In the second bit of work, we actually go to a soft cutoff functional RG scheme where we don't have to write Landau damping in by hand, and we can see something that looks like Landau damping develop as the theory is renormalized. So I'll tell you to what extent it looks like Landau damping when we get there. So in this first calculation for A, we're doing more or less what I pointed to before. So a set of fermions with a linearized dispersion, a set of bosons with a mass m. We don't need to write a frequency-dependent term for the bosons because they'll pick it up from the fermions anyway. And a Yukawa type interaction. This time we're doing the ferromagnetic case. So this is really the spin density of the fermions interacting with the magnetic fluctuations. And we're doing it within this language of functional renormalization group, which is different from conventional renormalization. In conventional renormalization, you start with an ultraviolet cutoff. And what happens when you lower that cutoff is that you gradually integrate out the degrees of freedom in the theory until you get a sort of deformed theory which describes the remaining low energy degrees of freedom. In functional RG, you have a scale which, as you reduce it, gradually exposes the singularities in the Green's functions and smoothly maps your ultraviolet action, which is non-interacting, the microscopic action basically, down to the appropriate action for the low energy theory. Now, this is often described as an exact RG, and if we could actually solve this equation, it would be. But actually, in order to make a practical calculation, one always has to parameterize the effective action appearing in this theory, and that parameterization of the effective action is typically an uncontrolled truncation. So I mean, beware of that. The literature will tell you that this is a kind of exact RG, and many bits of the literature sing its praises, and they're not wrong. But to actually implement it in practice, you need a truncation, and the truncation is often just an uncontrolled restriction to a subset of terms that you think might come up physically. And that's certainly where we are here. So what we do here is to say, okay, we restrict ourselves to the lowest order diagrams. That doesn't mean that the method is perturbative. It just means that our parameterization is based on the form of those lowest order diagrams. And so we allow the frequency-dependent term for the fermions to renormalize, the momentum-dependent term to renormalize. The problem with FRG for Landau damped systems is that, well, precisely because Landau damping doesn't come from an ultraviolet divergence of a diagram, you don't get any flow from this diagram in a hard cutoff FRG. And so we copy Lee, Strack, and Sachdev, who said, well, what you should do in the face of this is instead just determine the self-energy of the boson at every scale by just working out what this particle hole bubble is at every scale, and that will be the leading contribution to the self-energy of the boson. So that's exactly what we do. We say that this prefactor in the Landau damping is determined from the particle hole bubble at that scale. And there's a flow equation for the Yukawa coupling. This one does flow because there's a bosonic line in it, and so that has some regulator dependence. We get a closed flow equation for the couplings. I don't want to belabor this because I want to sort of tell you the point, but if you want more details, please ask, or they're all in the paper. And the upshot is we find a new fixed point for these FRG equations, where the anomalous dimensions of the frequency and the Yukawa coupling are non-zero. The anomalous dimension of the fermion momentum dependence is zero. There is a finite value of the dimensionless coupling at this point. So it's an interacting fixed point between the fermions and the bosons. And basically we get the following forms for the propagators of the fluctuations at this point. The bosonic fluctuation, the bosonic propagator has a Landau damped form, except that this power that used to be 1 in the perturbative case is now 3/5. The q squared is as it was. And the fermions are non-Fermi-liquid, but with another exponent, omega to the 10/13, which is not exactly the 2/3 that one gets from Hertz-Millis theory, nor is it exactly the 3/4 that one gets from the Fitzpatrick et al. Theory, but you can see that it's in the ballpark of both of those. And the momentum dependence of the fermion propagator is not renormalized. So if we ask what's the dynamical exponent of this theory, well, to keep these two terms competitive under renormalization, we would have to scale omega like q to the power 2 plus 3/5, which is 13/5. So the bosonic dynamical exponent is 13/5, and the fermionic dynamical exponent is 13/10, which is half of the bosonic one, which is sort of what you'd expect. So what does this mean? Well, naively, it means that there would be a weak power law divergence in the specific heat with temperature as you approach this fixed point. So C would go like T to the 10/13, just this exponent here. So C over T will go like T to the minus 3/13. Now that's not exactly the logarithm that was claimed in experiment, but a weak power law divergence is not so different from a logarithm, and so maybe we're not so far off the truth here. And this also predicts a rather unusual behavior for the damping rate of magnetic fluctuations. So previously our damping rate went like mod q, now our damping rate goes like mod q to the power 3/5. So the exponent there has been renormalized, reflecting, I think, the fact that the fermions are now not Fermi-liquid, and so they don't just move at a single Fermi velocity. So the perturbative expression for Landau damping is not going to be right. Okay, let me just say a few points about that calculation, and then I'll use my last few minutes to present the second one. One of the things that always kind of bothers me about these calculations is that if you hold the boson, so you might ask, well, the bosons do have mass. What are you doing about that? And what people normally do actually is just force the boson mass term to identically 0 at every stage in the flow. And of course, that's not really right, because the boson mass would flow under renormalization. So it shouldn't be starting at 0. It should be ending up at 0 when you reach the critical point. And so we're in some sense distorting the RG flow by holding the mass always 0. It would be nice to find some way to improve that. The fact that we don't have a cutoff in the fermion propagator because of the technique we're using could lead to singularities in the multi-boson vertices. In other words, we might not be any better off here than Hertz-Millis. We might have similar singularity problems, or at least equally severe singularity problems in the interactions between the magnetic fluctuations themselves. And also, again, we're suppressing superconductivity just as earlier authors did, and it would be nice to look further into that. But the real problem, or the thing I don't like so much about this calculation, is the way that in a sense we have still put Landau damping in by hand. Because what we have said in setting up this calculation is that the self-energy for the boson is going to have a perturbative Landau damped form, and we're just going to get the prefactor of that from the particle hole bubble at each stage in the renormalization treatment. What I'd really like is to see that move away from z=1 scaling emerge during the renormalization. And so in an attempt to do that, my student Matt Trott and I started exploring the possibility of doing functional renormalization group with soft cutoffs. So rather than completely removing the singularity in the Green's functions and then slowly revealing it by moving a hard cutoff downwards in energy. In this calculation, we try to use a cutoff which is soft in its frequency dependence, and so it can actually see the singularity to some extent even at the beginning of the renormalization group flow. So we are starting here with undamped bosons, and we'd like to see the damping develop. So you see here we have the same kind of free fermion action that we had before, but now we have a bosonic action which has an omega squared and a q squared. So we're using the undamped frequency dependence, and we just want to see what develops. And this is the mass term, delta tilde, which of course we're going to set to 0. And we have the Yukawa coupling here. And in this calculation, actually, we also track the interaction between the magnetic fluctuations, this 4 boson term here. It turns out that it's very important for this calculation that we retain not just the Fermi momentum, which is the radius of the Fermi sphere, but also it turns out that to get non-divergent answers, basically, you end up having to also make reference to the upper momentum cutoff for your Fermi-liquid theory. So we're assuming that our fermions are described by Fermi-liquid theory, but if we send that ultraviolet cutoff to infinity, we get a load of divergences. And that's sort of physical in a way, because KUV can't really be larger than KF. The Fermi-liquid theory has to fail before you get to the center of the Fermi sea. And so we'll see that an important parameter in our theory is the ratio between KF and KUV. And you can think of that in a way as dividing the Fermi surface into patches. I know I was not rude, but I was skeptical about patch theories earlier. It's interesting to see that in this calculation where we didn't explicitly introduce a notion of patches, that kind of notion appears anyway, actually, because this ratio between KF and KUV appears naturally in the calculations. And it turns out to basically represent the number of patches into which the Fermi surface can be divided on this KUV length scale. So we set that problem up. Crucially, we regulate the fermions with a soft regulator. So the fermion regulator takes this Lorentzian form, which means that, so the width of the Lorentzian is our kind of regulator parameter, and as that gets smaller and smaller, this regulator eventually goes or this chi eventually goes to 1. And basically that's just a way of putting in a regulator which instead of at each scale just introducing a little bit of the Green's function at that frequency, smoothly turns on the whole Green's function in a way that this function describes. A result of that is that we get, I haven't presented the flow equations because I knew I wouldn't have time to do so, but it's all in the paper, and feel free to ask if you want me to show them. But what we find is that we get a fixed point, we get a non-trivial fixed point for any value of this KUV, but its properties vary smoothly as we change this effective number of fermion degrees of freedom relative to the number of boson degrees of freedom. So we did this analysis for an arbitrary number of boson flavors just to see what we could see. So if there's only one flavor of boson, then we find that the anomalous dimensions evolve smoothly as we crank up the number of fermion degrees of freedom. When the fermions are dominant, so there are many more fermionic degrees of freedom than there are bosons, we find a boson anomalous dimension of 1 and fermionic anomalous dimensions of 0, which of course makes sense. If the system is dominated by the fermions, their properties won't be altered, but the properties of the boson will be altered because it has many types of fermion to scatter from. And so we see a bosonic dynamical exponent of 2 over in this limit, and well, we can't get right to the other limit, but if we extend it beyond here, it will be going down to 1. This is perhaps more instructive. So this is a plot of the evolution of these anomalous dimensions as a function of the number of boson flavors for a fixed number of fermion patches. And as you see, what we're seeing here is actually a crossover between 2 different types of fixed point. When the number of bosons is large, then the bosons return to to basically undamp Z equals 1 bosons, and then we get non-Fermi-liquid behavior, so we get non-trivial anomalous dimensions for the fermions. In the other limit, the fermions approach a Fermi-liquid behavior, and the bosons approach this kind of Z equals 2 scaling. And so here's the crossover in sort of physical exponents. Z is the dynamical exponent, nu is the correlation length exponent. The correlation length exponent's interesting because it's a half in both of the two limiting cases, but it bumps up to a larger value in between. The dynamical exponent, as I've already mentioned, is 1 in the boson-dominated case, where Landau damping doesn't really get going, and it evolves smoothly to 2 in the fermion-dominated case. I note, just as a comment really, that this dynamical exponent of 2 appears to match what was observed in quantum Monte Carlo treatments of the nematic quantum critical point by Shatner, Lederer, Kivelson, and Berg. They conjectured that they hadn't got into the scaling regime in their numerics, I guess because they didn't really believe that the dynamical exponent was 2. But I think it's interesting that this calculation does produce a dynamical exponent of 2 right at the critical point in the case where the number of fermion flavors is dominant over the number of boson flavors. Another thing this tells us is that the exponents might not be universal. I mean, I guess one of the nice features of the Hertz-Millis predictions was that, you know, there was one exponent predicted for the ferromagnetic case, one exponent predicted for the antiferromagnetic case. So this approach would tell you that that might not be right, because which dynamical exponent I get in this case depends on a non-universal piece of information, which is the number of effective fermionic degrees of freedom I have. And that depends on 2 non-universal things, not just Kf, the size of my Fermi surface, but also the scale at which my Fermi-liquid theory, you know, ceases to apply. So that might suggest that we could expect some lack of universality in the exponents at these points. Or at least that's what we see in this calculation. So let me conclude. I'm a little bit past the time I was aiming for, but not too bad. So a discussion. I've shown 2 calculations that we did within the fermion boson model that include Landau damping at some level. There was a hard cutoff functional RG. That has the disadvantage that we don't really generate Landau damping in the flow. It requires self-consistent determination of the bosonic self-energy at each scale. In a sense, therefore, you might say it's not really a proper RG at all. It does, of course, yield Landau damping because, in a sense, we put that in. And we do get an interesting renormalized dependence of the damping rate on momentum. And then in the second part, I showed a soft cutoff functional RG, and that actually showed a crossover from dynamical exponent 1, which is the undamped case, to dynamical exponent 2, which is damped but not with the conventional exponent. And that's as we rebalance the number of the fermionic degrees of freedom relative to the bosonic ones. And the punchline basically is that we get non-universal exponents in that treatment, which are dependent on a microscopic scale, which is sort of theoretically ugly, but it is reminiscent of experiment. It's not true that all of these materials show the same exponents, even materials that you would naively have said should be in the same universality class. So maybe we should take seriously the idea that something like the ultraviolet validity scale of the Fermi-liquid theory is playing in. Just a brief mention of outlook. To my mind, the real question that this raises is what even are the rules for formulating an RG scheme in this kind of problem? So we have this sort of Shankar RG where you renormalize down to the Fermi surface, which is perfectly good for problems where the fermions are the only degrees of freedom, but it doesn't work, at least not straightforwardly, when mixed fermionic and bosonic degrees of freedom are present. And then the third bullet point is the point I've already made. Maybe we're talking more a floating point than a fixed point. Landau Fermi-liquid theory is a sort of floating point. It's not a single fixed point. You have all these infinitely many Landau parameters, which can be different in different Fermi-liquid theories. In Landau's theory of the Fermi-liquid, varying those parameters doesn't affect the exponents that you see, but perhaps in fermion boson theories it does. And our soft cutoff calculation, if there's anything to it, suggests that that might be the case. And obviously, we haven't discussed superconductivity at all, and that is something that we ought to discuss. So, to summarize, We've observed that many materials exhibit non-Fermi-liquid behaviour, lack of quasiparticles, strange exponents near their quantum critical points. We've pointed out this is usually understood in terms of strong scattering of conduction electrons from slow fluctuations of the order parameter. We pointed out that it's hard to include damping in this picture in a consistent way, especially when the order is spatially uniform. And I guess our contribution, following Subir and colleagues, is to point out that functional renormalization group methods provide an interesting new way of doing these calculations. The results are sort of intriguing, but I think it's fair to say that we still don't really know what the scheme should be for setting this calculation up properly. Okay, that's it from me. Thank you very much for your attention.
Okay, so if anybody has any questions, they can just either unmute themselves and ask them. So Professor Sachdev, you have a question, so why don't you go first?
Okay, hi Chris, very nice talk, thank you.
Thank you.
So I have a couple of questions about the soft cutoff calculation you mentioned at the end.
Yeah.
One is, does the calculation actually give you a critical point or a critical phase? That is, do you actually find that you have to fine-tune one coupling to reach the critical behavior, and otherwise it's just a Fermi-liquid, or it always flows to a critical phase?
No. So the mass term is relevant.
It is relevant, and you have to tune it.
Yeah, no. So you do have to tune the mass to 0 to reach the critical point.
Okay, and my other question was, you have this variable exponents, which you mentioned depend upon kf over kuv.
Mm-hmm.
Do they also depend on the shape of your cutoff?
So my guess is that the answer is yes, but we haven't checked. So yeah, clearly that's a piece of work that needs doing, and we just haven't, well, Matt went off to work on different things, and we ended up thinking about vanadium diselenide, but it's clearly a piece of work that still needs doing to look at the cutoff dependence. Actually, Matt worked with Litim before coming to me, and the work he was doing there was looking at the dependence of on the form of the cutoff of various properties, but that was in different kind of high energy theories. So the answer is I don't know, but I suspect that it is dependent on the form of the cutoff. I'm faintly hopeful that what that will affect is the form of the crossover between these two limits. I'd be surprised if an integer of exactly 2 in this limit and exactly 1 over here, those feel as if they should be robust. But we haven't checked that statement.
But well, you choose some fixed value of NB, and then you do the RG, and you find a fixed point. I mean, everything just settles down to the same shape.
There is literally a fixed point. We numerically solved the equations to check, but actually you can determine the fixed point analytically. So, but we have also numerically solved the flow equations, and indeed it always goes to the fixed point that our analysis shows.
Wow. Okay, thank you.
Thanks.
Any other questions? So either you can raise your hand or you can just unmute yourself if you have a question. Okay, so maybe I have one question. So this might be a naive question, but do you consider any anomalous scaling dimension of the charge density operator?
Is the motivation behind that question thinking about other possible orders that could be developing? Yeah. Yes. So no is the answer. Mm-hmm. This is not the kind of FRG calculation where you do kind of multi-channel and you try and follow their competition with each other. We have recently done a couple of calculations like that on kind of strong spin orbit coupled materials near Van Hove points and so on. But no, this is not one of those. So here the focus is really on trying to describe the non-Fermi-liquid. We thought the simplest context in which we would see that is concentrating on a single type of bosonic fluctuation. But I mean, of course, it's possible that competition between multiple types of fluctuation also affects the form of the non-Fermi-liquid. If that's true, then we can't see it in this calculation, but it would be interesting to try to extend it to include that.
Okay. And the other question I had was, could you go to slide 36, please? I believe it was.
Sure.
Yes. So you're saying that your last bullet point, ferromagnetism and superconductivity should compete anyway. So this may be right.
Yeah. So this is what I'm thinking of here is the stuff by Rousseff and Millis about 20 years ago. So this suggestion that when you're approaching a ferromagnetic quantum critical point, you have transverse and longitudinal magnetic fluctuations, and some of those are pair breaking and some of those are pairing. And so as you approach the quantum critical point, you have to ask, well, which is winning? So, and if the pairing fluctuations are winning, then you'd expect a single superconducting dome shielding the critical point. If the pair breaking fluctuations are winning, then you'd actually expect to see a sort of divided superconducting dome with TC dropping to 0 exactly at the quantum critical point. And certainly the Rousseff-Millis paper suggested that that was the scenario that you'd actually get. If that's true, then actually the quantum critical region directly above the quantum critical point to ferromagnetism may not need us to think about the instability to superconductivity, because TC has been pushed to 0 at exactly that value of the boson mass.
I see. But see, in some materials like uranium, germanium, ferromagnetism and superconductivity can coexist.
Of course, that's completely right. So, yeah, there are lots of questions to ask if you want to see how these theories might directly relate to materials. And certainly there are plenty of ferromagnetic materials that have what look like quantum critical points where the superconducting phase does retain a finite TC over the critical point. There's a lot more to say about those, though, I think. And I mean, once you start to entertain the idea that there might be non-universal aspects to these things, uranium is definitely a very worrying element to have around. Right? So I think the cerium and the ytterbium-based heavy fermion materials are an order of magnitude simpler in their phenomenology than the uranium-based ones. So if a uranium-based material doesn't do what my simple theory says, my own feeling is I'm not going to worry about that a lot. If it doesn't fit any of the cerium or ytterbium ones either, then perhaps I should be more concerned.
Okay. So any other questions? So please unmute yourself. So maybe I'll wait 5 seconds. Okay. So let's thank Professor Hooley again.
Excellent.
Oh. Okay.
Great. Thanks for the invitation.
Welcome.
Good to see you.
Yeah, likewise.